Pathogenesis, host defenses, and antiviral drugs, presented by Taylor Garner. I'll be giving an overview of 3 key chapters that build the foundation of our understanding of viral infections, how we combat them, viral pathogenesis, host defenses, and antiviral drugs. First, we'll look at how viruses invade, replicate, and cause disease within the body. Then we'll shift to the host perspective and explore the immune mechanisms that protect us from viral attack, including both innate and adaptive responses. Finally, we'll connect these concepts by examining antiviral therapies, how they work, why they're effective, and how they've transformed the treatment of many viral illnesses. Together, these chapters provide a clear picture of the complex interaction between viruses, the human body, and the medicines designed to keep infections under control. Pathogenesis is the ability of a virus to cause disease, and it has 2 distinct levels. The first level is the changes that occur within individual cells, and the second is the process that takes place in the infected patient. Within the individual cell, there are 4 main effects. Viruses can ultimately damage cells and tissues through cell death. Viruses inhibit host cell protein synthesis. The cell will stop making its own proteins and start making viral proteins instead, so the virus takes over the cell. The cell then dies while the virus reproduces and spreads. The next main effect of viral infection on the cell is the fusion of cells to form multinucleated cells. When viruses cause infected cells to fuse with neighboring cells, they create large multinucleated structures. These fused cells are abnormal and cannot perform normal cellular functions, which disrupts the tissue's overall integrity and efficiency. Multinucleated cells are also unstable and often die prematurely, contributing to tissue damage. In addition, the formation of these cells allows the virus to spread directly from cell to cell without being exposed to the immune system, making the infection a lot harder to control. Next, we have malignant transformation, which occurs when certain viruses alter a cell's genetic material in ways that drive uncontrolled growth and division. These viruses may insert their own genes into the host genome, disrupt tumor suppressor pathways, or activate oncogenes that push the cell toward a cancerous state. As a result, the transformed cells no longer respond to normal regulatory systems and begin to proliferate abnormally, forming tumors and invading surrounding tissues. This unchecked growth not only damages the affected organ, but can also spread throughout the body, posing serious health risk. Lastly, there are some instances in which viral infection causes no obvious morphologic or functional change in the infected cell. These are often called latent infections, where the virus remains inside the cell without killing it or disrupting its normal activities. Although the cell appears healthy, it silently harbors the virus, allowing it to evade immune detection and remain in the body for long periods. This state can still be harmful because the virus may reactivate later, spread to other cells, or contribute subtly to long-term tissue damage. Even without visible changes, these hidden infections play an important role in chronic viral diseases. The other distinct level of pathogenesis is the process that takes place in the body. First, the virus has to be transmitted and enter a new host. There are several different routes of transmission for viruses, including respiratory droplets, direct contact with bodily fluids, contaminated surfaces, ingestion of contaminated food or water, and vector-borne spread from insects like mosquitoes or ticks. After entry, the virus must establish infection by attaching to and entering susceptible cells. Once replication begins, the next key step is the spread of the virus to other cells and tissues, which determines how extensive the infection becomes. Finally, the innate and adaptive immune responses play a major role, not only acting as essential host defenses to control and eliminate the virus, but also sometimes contributing to disease when inflammation and immune-mediated damage become excessive. I have discussed how viruses affect the body. Now we will talk about how the body works to combat these viruses. When a virus attacks the body's first line of defense against them relies on nonspecific or innate immune mechanisms that respond immediately to infection. These physical barriers, such as the skin, mucous membranes, as well as physiological defenses like acidic environments and digestive enzymes that inhibit viral survival. Once viruses breach these barriers, innate immune cells, including macrophages, dendritic cells, and natural killer cells, recognize general molecular patterns associated with the viral infection. Interferons play a critical role by signaling neighbor cells to heighten their antiviral defenses by slowing viral replication. Although these responses are not tailored to a specific virus, they act rapidly and are essential to containing early viral spread. Specific or adaptive immunity provides a more targeted response once the body identifies the particular virus involved. This system relies on B cells and T cells, which recognize viral antigens and mount a precise defense. B cells produce neutralizing antibodies that block viral attachment and entry, while cytotoxic T lymphocytes destroy virus-infected cells to halt further replication. Memory B and T cells are also generated, allowing the immune system to respond more effectively and quickly upon future exposure to the same virus. Although adaptive immunity takes longer to develop than innate defenses, it is critical for clearing many viral infections and forms the basis for long-term immunity and vaccine protection. When the body is not capable of clearing a virus on its own and the infection persists, antiviral drugs may be needed to help control viral replication and reduce disease severity. Unlike antibiotics, which directly kill bacteria, most antiviral drugs work by interfering with specific stages of the viral life cycle, such as entry into host cells, genome replication, or viral assembly. These medications are particularly important for infections that can be chronic, cause severe illness, or have limited treatment options, providing a means to manage symptoms, prevent complications, and reduce the risk of transmission. There are several classes of antiviral drugs, each targeting different viruses or stages of infection. Nucleoside analogs inhibit viral DNA synthesis and are commonly used against herpes viruses. Drugs like zanamivir target influenza viruses by blocking neuraminidase, preventing viral release from infected cells. For chronic viral infections such as HIV, combination antiretroviral therapy includes reverse transcriptase inhibitors, protease inhibitors, and integrase inhibitors to suppress viral replication effectively. Additionally, newer drugs target hepatitis B and C viruses, offering direct-acting antiviral therapies that can lead to viral clearance. These examples show how antiviral therapy is tailored to specific viruses and stages of infection to optimize effectiveness. The effectiveness of antiviral drugs is guided by several key principles. They are most effective when they target specific stages of the viral life cycle, minimizing harm to host cells. Because viruses replicate inside hosts, drugs must selectively interfere with viral processes without causing excessive toxicity to the patient. Resistance can develop if viruses mutate, so proper dosing and combination therapies, especially for chronic infections like HIV, are critical to maintain efficacy. Finally, antiviral therapy is often tailored to the individual patient and the specific virus, taking into account disease severity, immune status, and potential side effects. Understanding these principles helps clinicians choose the most appropriate therapy and maximize patient outcomes. In conclusion, understanding viral pathogenesis, host defenses, and antiviral drugs provides a comprehensive view of how viruses interact with the human body and how we can intervene. Pathogenesis explains how viruses cause cellular damage and disease at both the cellular and systemic levels. Host defenses, including innate and adaptive immunity, are critical for controlling infection, though they can sometimes contribute to disease severity. When the immune system is insufficient to clear an infection, Antiviral drugs offer targeted strategies to inhibit viral replication, limit disease progression, and prevent transmission. Together, these concepts highlight the dynamic interplay between virus, host, and therapeutic intervention, emphasizing the importance of both prevention and treatment in managing viral diseases. These are the references that were used. Thank you.